So now let us understand the quantitative view of the second quantization of light. To understand it, we need to understand the semi-classical treatment of light, and let us refresh our ideas about the semi-classical treatment of light over before moving on to the quantization of light. So the dynamics of the electromagnetic field in the semi-classical treatment of light in free space is given by what are called as the Maxwell equations. These are the four set of equations which are used to describe the movement of light in free space. Apart from these electromagnetic and electric and magnetic fields, we also have what are called as the magnetic vector potential A bar and the electric potential phi. Both of these also help us determine how these electromagnetic fields propagate, and numerous equations in electromagnetism can be expressed either in terms of E bar and B bar, or alternatively in terms of the potentials phi and A bar. However, in more advanced theories like quantum mechanics, the use of the potentials it predominates the use of the uh, fields. Now, there is one caveat when we use the potentials. These potentials are not unique, and it is defined up to the gradient of a scalar function. This non uniqueness is referred to as a gauge freedom, and different choices of these vector potentials can lead up to the same kind of dynamics or physical situation. So, we have something called as a gauge freedom. Now, if we fix a particular gauge when doing a theory, we can go ahead and get a particular idea. So choosing a gauge can sometimes help in simplifying equations. Now, in terms of the vector potentials, A bar, the electric and the magnetic fields can be written as given by these equations, where these phi is the scalar potential and A bar is the magnetic vector potential. Now we are using here what is called as the Coulomb gauge. Now, using these relations and the Maxwell's equations that we defined here, we can derive this particular equation regarding the magnetic vector potential. Now, if you look at this looks nothing but like a wave equation. You may have encountered this wave equation when we studied basic electrodynamics, and I highly recommend you to refreshen up to understand this in more detail. The solution to these wave equations is given by this particular equ- equations. These are planar wave equations, planar solutions. Sorry. Now let us understand these planar solutions. So this is the a particular solution of the magnetic vector potential, which when substituted here on the left hand side will give us 0 on the right hand side. Now, all these kind of planar wave solutions are legitimate solutions of this wave equation. There are two factors on which it will depend. One is the k bar and the second is alpha. Now, let us understand these one by one. So, whenever we talk about a vector field, if we want to understand it, we should understand that this field is defined at each and every point in space time. So, at each and every point in space, this particular field exists. However, here I am putting separate dots, but you should understand that this is for pictorial purpose. Now, at each and every point, you can assign a vector. This vector, the direction in this vector points to, is called as the polarization of that particular field. It is given by this particular vector epsilon bar k bar comma alpha, where alpha is equal to plus minus 1, and it denotes the right circularly polarized light or the left circularly polarized light. I'll come to it. And k bar, it denotes the direction in which this particular wave is moving, and it is also hence called as a propagation wave vector or the propagation vector. Now alpha equal to plus 1 denotes that these vectors are moving in a right circularly polarized way in space. So at, at this point, if this is the wave vector, this is the polarization at this point 1, then the polarization at this point 2 is in this direction, and at 3 is in this direction. So it's kind of moving in this manner. Alpha equal to minus 1 denotes the left circularly polarized light, that the light, the wave vectors, while propagating, are moving in this direction. Now, using these two, we can define all other polarizations. That is why we use it as a basis. Next, this particular value, La, is a scalar value, complex amplitude. It is called as a complex amplitude of this plane wave solutions. And this R bar here denotes the position at which we are trying to find the value of this vector potential. So if this is, these are the coordinates, this is the origin, then this particular point, this r bar, is a position vector of the particular point at which we want to evaluate the magnetic vector potential. And t is time, and these omega is the oscillation angular frequency for this particular wave vector k. Now this wave vector is also called as, you can also name them as modes of this light, and the magnitude of this wave vector is given by these relations: 2 pi nu by c, where nu is the frequency of the light and c is the speed of light. And then if we write this 2 pi nu as omega k, then this is equal to omega k by c, and using the relation between that c is equal to nu lambda, we can also derive this relation, that is c mod of k bar is equal to 2 pi by lambda. Okay, so now let us consider a problem that we have light which is confined in a cubical box like this. So we have a cubical box, and outside it the light cannot go away. It's perfectly like trying to restrain the light inside it, and all the sides are equal to L. Now in this particular box we will only have certain allowed wave vectors k bar, also called as modes. Only certain modes which will be possible in this particular cubical box. It is similar to this particular problem where we have a string attached to two walls, and these walls are separated by a distance L. And if I pluck this string, then only certain types of oscillations are possible in this particular system. So they are denoted as first harmonic, second harmonic, third harmonic, and mathematically denoted, the frequencies are denoted as F1, F2, F3, and these are the relations between those frequencies. And the values of the possible wavelengths in this particular setup are 2L, L, 2 by 3L, and so on, where L is the distance between these two walls where the string is attached. And the possible wave vectors or modes are these 2 pi by lambda, sorry, are these pi by L, 2 pi by L, 3 pi by L, and so on. So, coming back to our problem of this light confined in a box, the allowed modes are given by these values: kx equal to 2 pi n x by L, ky equal to 2 pi n y by L, kz is equal to 2 pi n z by L. Now we have these three allowed modes, because values, numbers, because we are working in 3D rather than 1D over here. And these nx, nys, and nz's are 0, plus minus 1, plus minus 2, and so on. Now, in this particular problem of light confined in a box, the magnetic vector potential takes this particular form. So, A bar is the sum of all possible modes. The magnetic vector potential A bar at point R bar and at time t is the sum of all possible modes like these. And then using this and the Maxwell's equation and the relations between the magnetic vector potential and the electric and magnetic fields, we can derive these formulas easily. I'll not go through the details or the derivations. You can find them online, or you can just do it by yourself. It's not that hard. So now, using these values, we can derive the total energy of the light field inside the box. So, in electromagnetism, classical electromagnetism, this is how we define the energy of the radiation. Now, using these relations between E bar, B bar, and the magnetic vector potential that we saw here, we can derive that H, that is the total energy of the radiation field, is given by this particular relation. And this we can write in a simplified form like this, where this ek bar comma alpha are these values. So here now we have understood the classical electromagnetism and how the electric field and magnetic field can be written in terms of the magnetic vector potential and the magnetic vector potential solutions for light confined in a box. Now let us understand what happens when we quantize this semi-classical treatment of light. Quantize the electromagnetic field. Now the best example of quantization is the replacement of the time-dependent linear momentum of a particle by the operator form as given on the right hand side. For the electromagnetic field, we will do something similar. The magnetic vector potential complex amplitudes A and A star, these things here, we will replace them by operators A cap and A cap dagger. By using this kind of a transformation, the semi-classical electromagnetic vector potential now becomes quantized and is written in this manner. The electric and magnetic fields are given by these expressions in the quantized form. And the energy, which needs special attention, is now in the quantized form, looks like this. Now you may see this, it is similar to the Hamiltonian of the quantum harmonic oscillator. This particular form is like having A number of non-interacting independent one-dimensional harmonic oscillators like these, each with its own fundamental frequency, omega k bar. So each of them has some fundamental frequency, omega k. They can be different. Now, because these oscillators are independent, the Hamiltonian is a simple sum. Now, it turns out if we consider Fock states, so what are Fock states? We will bunch uh, all the harmonic oscillators. Let's say ones having the omega k to be equal to 2, let's say. So we will bunch them together and call that omega equal to 2 leads to n equal to 4 particles. So n 2 n uh, omega k or k n omega k, or you can replace omega k with k equal to 2 is equal to 4. So when we bunch these way the number of particles, we will form what are called as Fock states, and the representation of such a state can be given in this manner, where nk1 bar represents the number of particles with in the mode k, nk2 represents the number of particles in the mode k2, nk3 represents the number of particles in the mode k3. Now we see that this particular Fock state is an eigenstate of the Hamiltonian, because if I act this Hamiltonian on this Fock states, it can be expanded in this manner, and in the end we get a scalar like this multiplied by the state itself. So we see that this Fock state is an eigenstate of the energy operator of this particular setup of the radiation field inside the cubical box. As I had said earlier, you can think of these Fock states as the number of particles in this particular string k1 bar, the number of particles in this particular string k2 bar, and so on. These strings represent what are called as modes. Now, when there are no particles in all the strings, then we can represent the Fock state in this manner, and this is called as a vacuum state. It also has physical meaning, and there is some dynamics going on even when there are no particles. It is called as vacuum fluctuations. I highly recommend you to look into these videos by Emmanuel Bloch to have a more detailed understanding and look into the derivations. I'm not going into the detail because we are trying to have a more simplified view of the continuous variable quantum computing and the physical architecture behind it. So now, in all, if I want to compare the semi-classical and the quantum treatment of light, then if this on the left hand side is the expression for the vector potential, then this is the expression for the vector potential. Now it has been turned into an operator in the quantum version of the electromagnetic field or electromagnetism. And these are the transformations for the quantization. Now, if this is the expression for the electric field, then this is the expression for the electric field in the quantized version. If this is the expression for the magnetic field, this is the expression for the magnetic field in the quantized version. If this is the total energy of the radiation in volume L, V equal to L cube, then this is the total energy of the radiation in the volume V equal to L cube in the quantized version of the electromagnetic field. Now you see that these Fock states are eigenstates of the energy according to this expression. But however, in general, Fock states are not eigenstates of Hamiltonian, but they are eigenstates of the number operator. We had seen what are number operators earlier when we were studying the quantum harmonic oscillator. There are instances when these number operators when these Fock states are not the eigenstates of the Hamiltonian or the energy operator. They can happen when we have these kind of conditions. But for this continuous variable quantum computing architecture, or the physics behind it, we will confine ourselves with these kind of systems and not complicate things.